Yes.
Wonderful, thank you. So we're gonna move into the portion of the presentation tonight to discuss Moultonborough Bay and Winter Harbor and the watershed management plan that we've been working on over the last few years. So I first just wanted to introduce our project team tonight. You just heard from Pat Tarpey. So for anyone who's new or listening in on this meeting, Pat's the executive director and the project lead for this grant from the Lake Winnipesaukee Association. And my name is Maggie Mills, and I'm a project manager at FB Environmental, which is a small consulting firm, and I'm in Portland, Maine. And my colleague, Laura Deemer, who's the water quality monitoring and modeling lead at our company, is in the Portsmouth, New Hampshire office. And we collaborated on this project with Don Kretschmer on the modeling. And Don is a local, so you might know him. And he's also a New Hampshire certified lake manager. And after Laura and I speak, Brian Leverrier from Horsley Witten Group will be joining us. And Brian is a landscape designer, and he will be talking about some of our best management practice ideas that came out of this project. So our agenda tonight, we're gonna first start with an introduction to watershed planning, and we'll then talk about the Moultonborough Bay and Winter Harbor watersheds. We'll talk about the characteristics of those watersheds, the current water quality data, pollutant source identification, and then looking ahead at future possible sources. And then once we go over that, we'll talk about setting water quality goals and targets for achieving those goals. And finally, we'll move into recommendations and planning for the future and kind of, what the purpose of this plan is. And following that portion of the presentation, Brian Leverrier will present on those engineered designs as I just mentioned. Okay, so we're here tonight to discuss these watershed plans. So what are watershed plans? So the US EPA has funds available through the Clean Water Act. And what these funds do is they provide money to lakes and associations that are experiencing impairments from non-point source pollution. And so each of these plans adheres to this EPA format, and they have 9 specific elements, and our plans include those. So we'll talk through those generally tonight, but basically the purpose of those 9 elements is to make sure you're assessing your current conditions, you're accurately looking at potential threats and to the lake, and then you're making recommendations that are really going to move this lake forward in restoration. And what's really important is that watershed planning is a dynamic process. And so we can't think of this as a static plan. It's really a living document because we're here in this one snapshot of time for the lake and for these embayments, but they're changing, and we need to make sure that we're changing with them and understanding how they're changing. So here you can see it's a cyclic process. We'll just touch on this briefly. So we first established a steering committee, which Pat did for this group. So we have a committee of lake residents and town members who are guiding this process. We then go out and we complete field surveys, and we get an understanding of what's going on in the watershed and on the roads, at people's houses. What's the situation? We look at current water quality conditions in that water body, and we look at how those compare to state standards. We then can set some goals for the lake, and then we can move forward and create an action plan with specific strategies for achieving those goals. We finalize the plan. We work with New Hampshire DES and the Department of Environmental Services and EPA. And then having one of these plans allows you to unlock more funding from the EPA through this Clean Water Act funding. So as you know, tonight we're going to talk about Moultonborough Bay and Winter Harbor and their watersheds. So what you can see on your screen on the bottom left is the full Lake Winnipesaukee watershed, and in that light blue color is the surface waters. And you can see that in green and blown up to the right on your screen is the Moultonborough Bay watershed. So that's about 29,800 acres. And then in that reddish color below, you can see that we have the Winter Harbor watershed, which is much smaller at about 5,000 acres. And I just wanted to point out, Pat mentioned this when she spoke, and how the Lake Winnipesaukee Association is kind of moving around the watershed and doing these watershed plans. One that's very connected to this plan is the Moultonborough Bay Inlet watershed. So you can see on that image of Lake Winnipesaukee, the Moultonborough Bay Inlet watershed is in purple, and that's really important because it feeds into Moultonborough Bay. So water quality is very connected, and it's important to note that water quality in the full lake is very connected. This is a full lake system, so we're looking at a small piece of it, and we really have to remember that that's the context that we're working in. So when we look at states, we often talk about their trophic state. And so we just wanted to touch on this. Lake Winnipesaukee as a whole, and therefore Moultonborough Bay and Winter Harbor, because they are part of Lake Winnipesaukee, they're classified as oligotrophic, which means they have high quality waters. So you can see on the image, on your screen on the left, on the top we have oligotrophic water bodies. And what that means is that they're relatively clear, there's less plant life, there's less algae. And naturally, as a lake ages, we say it eutrophies. And so at the bottom, you have a eutrophic system. And so slowly over time, sediment and organic matter from the landscape makes its way into that lake, and it starts to decrease in water clarity. And we call that a eutrophic system. And what's important here is that this is a natural process, but in a lot of lakes, we see that this process is accelerated by human use. So despite being oligotrophic, Lake Winnipesaukee is listed as an impaired water body because of the occurrence of cyanobacteria. And one such cyanobacteria that's present in Lake Winnipesaukee, and specifically we've seen in Winter Harbor, is shown on the right, and that's Gliotrichia. So Gliotrichia is a freshwater plankton. It's about 1 to 3 millimeters in diameter. It's a type of cyanobacteria, and it can actually fix nitrogen to use as a food source. And sometimes these cyanobacteria can produce toxins that are called microcystins. So one of the phenomena that we've seen across New England and that researchers have seen in the Northeast is that we're seeing Gliotrichia showing up in these high quality waters where nutrients are somewhat lower. And so you can see the map on the right is from a 2012 study showing that Lake Winnie is not alone with Gliotrichia blooms. You might recognize the photos on the left. Those are from Don, and he took those on in Lake Winnipesaukee of a Gliotrichia bloom in the Broads. So this is really important because we have, this lake that has seemingly good looking water quality overall in state criteria, but something's going on here. So let's talk about that briefly. And it's already 7:08, so I'm gonna have to cruise here. So we have these 5 indicators we often use to measure water quality in lakes. And we look at these because it's too expensive and too time consuming to look at every single contaminant that we could possibly have. Wouldn't be feasible. So we can look at these 5 indicators. So we have temperature, which can be hugely important and stress aquatic life. It can also change how lake turnovers are happening and how mixing is happening by changing water density. We have dissolved oxygen, which is a measure of the oxygen dissolved in the water and available for aquatic organisms. We have water clarity, which we measure using a Secchi disc. So on your screen, you see that black and white disc. You lower that into the water and volunteers mark when they can't see it anymore. And that's a measure of water quality. And it's an incredibly powerful tool that's free if you have volunteers for tracking changes in water clarity. It can act as an indicator for, for example, an algae bloom. And then we have chlorophyll A, which is the green pigment in plant and algae. And so if we see a spike in chlorophyll A, it might be an indicator that there's something going on. And then most important in these plans is phosphorus. So phosphorus is the limiting nutrient in a lot of freshwater lake systems, meaning that algae can't grow without more phosphorus. So by adding phosphorus to the system, we're basically adding the food that they need to continue growing. So as Pat mentioned, and I'm not going to spend time on this because she did, there is a lot of sampling on Lake Winnie, but these two maps, we have Moultonborough Bay on the left and Winter Harbor on the right. We have 10 sites in the Moultonborough Bay and 12 in Winter Harbor. The blue represents the depth of the lake. So you can see that the Moultonborough Bay watershed is very complex with a bunch of different basins. And the Winter Harbor watershed is a bit more straightforward in its shape. So on a big picture scale, when we talk about lake sampling, we often use the deep spot of a lake as representative of water quality conditions. So to visualize this, we have, so to visualize this, we have this profile here of a lake. And you can see that if you think about the line on the horizon as the top of the lake and try to imagine it as going down in depth, that we can drive our boat out into the middle of the lake and we can lower that Secchi disc and see our clarity. We can also lower a core tubing and we look at the deep spot and we put that tubing down and we kind of have a core of lake water that we can then analyze and use that as representative. So when we do that in the basins of Moultonborough Bay and Winter Harbor, we can see that water quality is generally in those indicator parameters looking good. And on this big picture scale, that's what the state is going to look at. That allows them the resources to look at every lake, which is a huge effort. To visualize this, I have these two gradient scales. On the left, I have total phosphorus. And on the right, I have chlorophyll A. The top, we see red, which is poor water quality. And at the bottom, we see blue, which is excellent water quality. So the state sets standards for water quality. Now, I'm not going to go into this because we're going to run short on time, but you can see for phosphorus and chlorophyll A, this first line right here shows the state standard. And then the state applies a buffer of sorts to make sure if there are changes from year to year, that your lake's not going to tip over that standard, and that's standard for high quality water. So they apply this 10% buffer. And what we can see is for Moultonborough Bay and Winter Harbor, looking at those indicator parameters, water quality generally is coming out below those standards or towards the excellent side of the range for total phosphorus and chlorophyll A. And that's, I put a note here except for one Center Cove, which only has a very small sample size. So we don't want to make too many assumptions about that. So I wanted to put up another visual here for you to talk about what this means. So we see this original lake profile graphic that we just discussed in reference to the deep spot. So when we go out and we sample at a deep spot, we're making some assumptions, and we're assuming that that deep spot is representative of the lake and that there's relatively uniform mixing and lake processes occurring at that deep spot. But in reality, there are some nuances to this. And what we want to think about is those nuances. And as I mentioned, the deep spot is a really helpful tool, but the nuances can help us understand some of the specific issues that we might be seeing, and in this case, gliotrichia. So what I've added to this image is what's happening in reality. So in reality, you can see it's not just mixing in the deep spot, it's mixing in all these smaller locations. There's runoff coming in from the watershed. When precipitation happens, it rains, stuff comes off the landscape. And so we have to really think about these nuances in water quality as well. So just in summary, what we went over for water quality is that current water quality at the deep spots in Moultonborough Bay and Winter Harbor is good and meeting state criteria, but there's these nuances that are potentially causing these cyanobacteria blooms, and specifically it's listing as impaired in the gliotrichia blooms that we're seeing in Winter Harbor. And that complex basin shape that we saw in Moultonborough Bay and mixing with the broads and nearshore inputs can result in site-specific differences in water quality. So we have to take a larger picture. And future threats to water quality can also pose challenges for restoration. So now that we've looked at current conditions, let's talk about the watershed and possible pollution sources that could exist in that watershed. So this graphic includes some common pollution sources in lake watersheds. We call these nod-point source pollution because they represent a diffuse pollution source in the landscape. So non-point source pollution is coming from many different points, which is what makes it so challenging to address. A point source or a culvert entering a lake is really easy because you find it and you fix it. And so this slide just shows some typical pollutants that we see. We have dog waste, we have agriculture, we have septic systems, we have fertilizer, we have development and pavement with runoff. And so what we do is conduct a watershed survey in the lake. And so we did that for Moultonborough Bay and Winter Harbor watersheds. And through this survey, we try to identify areas that are likely contributing a disproportionate amount of pollutants to those surface waters. And what you'll see on this slide is just a few select images. And what's key is that sediment that moves from the watershed into the lake carries nutrients on it, such as phosphorus. And so if we have runoff or we have water that's carrying sediment, that is one of the biggest pollution sources that we see in lake watersheds. So in our field surveys in Moultonborough Bay and Winter Harbor, we identified a total of 107 sites that we thought could use a little bit of help or best management practices, as Pat mentioned earlier. 4 of these sites, we pursued technical designs with Horsley Witten Group, and those were just conceptual ideas. And then we elevated 3 of those designs for further consideration. Brian will speak of these more, so I'm not going to go into it now. But basically, we look at all the sites, we prioritize them, and then we tried to provide a stepping stone to move forward in that implementation. Because when we go into the watershed, we're looking from public roadways, we also go into the lake and we do a shoreline survey. And what that does is allows us a window into the effects of the direct shoreline on the lake. So we cruise around in boats, and Gloria and Allison, who were the AmeriCorps for Lake Winnipesaukee Association, were enormously helpful in this effort. They did most of this work. And so what you do is you cruise around the lake. We have a standard qualitative form that we turn quantitative, and we look at each parcel, every parcel in the shoreline, for its buffer or the vegetation that it has between the property and the lake. We look for bare soil, we look for erosion on the shoreline, we look for the distance of the structure to the lake, and we also look at the slope of the parcel. And so the purpose of this is not at all to finger point anyone as being wrong. As we said before, it's a combination of all kinds of sources, but it just allows us to use some of our grant funds and work with landowners to see where there might be ways that we can improve our lake shorefront. So in this survey, as a full team, and there was a lot of volunteer effort and, as I mentioned, effort from Gloria and Allison in this, 1,306 parcels were scored, and the scores ranged from 4 to 18. We had an average score of about 9.6 for Moultonborough Bay and 10.4 for Winter Harbor. And so basically we bin these into high, medium, and low priority. So we said anything above a 15 is a high priority site, Anything scoring between a 10 and 14 is medium, and less than that is a lower priority. And so what we've included on our presentation here is some questions to ask yourself about your property. And if you are, willing or interested in doing some work on your property, like certainly reach out to me or to Pat, and we can connect you with resources and ideas. The Lake Winnipesaukee Association also did a desktop inventory of septic systems for this project. So the average lifespan of a septic system is about 25 years. And so what we see is that 61% or 533 of the 870 houses within 200 feet of Moultonborough Bay were built prior to 1994. So this allows us to follow up and say, okay, so this is an old system. What maintenance has happened? What's the situation? And talk to the landowner. And we see that same thing in Winter Harbor with 67% of those homes with septic systems built prior to 1994. So with that, I'm going to turn it over to Laura for a few minutes to talk about some modeling we did with the lake.
Excellent. Thanks, Maggie. Next slide. So Dawn and I completed the lake nutrient modeling for the project, which I'll go over now. You've seen some version of this map before. The one on the left shows the full watershed areas of interest with Moultonborough Bay inlet flowing into Moultonborough Bay and Winter Harbor there to the south, both of which flow out into the Broads where there's fairly significant mixing through multiple outlets. The map on the right, Maggie, if you could click, zooms in a bit and shows the drainage areas for the major streams or lakes draining into Moultonborough Bay and Winter Harbor. For Moultonborough Bay, we separated out Melvin River, Wingate Brook, 20 Mile Brook, and 19 Mile Brook, as well as 6 direct shoreline areas around Moultonborough Bay. And then for Winter Harbor, we separated out Mirror Lake and the Basin, as well as 2 direct shoreline areas. Next slide. Now the model breaks down the phosphorus load to each water body by these 5 major sources listed in order as atmospheric, internal, waterfowl, septic systems, and watershed. Atmospheric deposition is phosphorus attached to sand or other small particles that get blown around and transported as dust and may settle on lake surfaces. Internal load is phosphorus that is released from bottom lake sediments when oxygen gets extremely low, which generally occurs in late summer. Waterfowl is direct deposition of large bird waste in the lake, like geese or ducks. And then septic system load is phosphorus leaching to groundwater within a short distance to the lake, about 250 feet. So just as Maggie said, LWA was able to compile records on the age and usage of septic systems within 250 feet of the shoreline, which we use to help estimate the septic system load. And then finally, the watershed load is derived from land use. So different land use types export more or less phosphorus per unit area. For instance, a developed parcel exports more phosphorus than, say, a forested parcel. In this particular case, the watershed load also includes the loads from the Basin and Mirror Lake for Winter Harbor, as well as Moultonborough Bay Inlet for Moultonborough Bay. And then we also assumed that a portion of the Broads mixes with Moultonborough Bay and Winter Harbor depending on wind and current directions. And this estimate is also included in the watershed load. Next slide. So here's a summary of the model results by the major source types that I just went over. Moultonborough Bay is shown on the left and Winter Harbor on the right. you can immediately see that the watershed load dominates for both. So 83% in dark gray for Moultonborough Bay and 61% for Winter Harbor. The other sources were smaller in their contributions. Internal load and waterfowl were relatively minor for both. Septic systems in the direct shoreline represent a small but significant fraction for Moultonborough Bay and a larger fraction for Winter Harbor at 12%. For the next slide, I'll be focusing on the land use breakdown for the watershed load. So just taking that dark gray portion of the pies that you saw on the previous slide. So here on the left, we're looking at the land cover breakdown just for Moultonborough Bay, most of which is forested, shown in green. 8% is developed, shown in gray. 3% is agriculture, shown in yellow, and 8% is water wetlands. So on the right, this pie shows the fraction of phosphorus load coming from each of these 4 land cover types. So the major point being that even though Moultonborough Bay watershed is only 8% developed, 35% of the phosphorus watershed load is coming from those developed land uses. Maggie, if you could click again. Similarly, for Winter Harbor, 17% of the watershed is developed, but contributes to 75% of the watershed phosphorus load. And this just illustrates the importance of ensuring appropriate land use zoning and regulations are in place to limit the impact that new and redevelopment projects have on the landscape and ultimately local water quality. Next slide. Another way to look at the model results is by phosphorus load per unit area in the major subdrainages. We grouped the values into 3 general categories, green being low phosphorus load and likely mostly forested, yellow being moderate phosphorus load, and orange being moderately high phosphorus load. Several basins emerged with the orange moderately high phosphorus load. So that would be the direct shoreline to Melvin Bay, 19 Mile Brook, Mirror Lake, and the basin. This is largely due to concentrated areas of development in those subdrainages. So for the plan, we had recommended that these areas be prioritized for future implementation work. Next slide. We also completed a build-out analysis for both watersheds. This was completed by Kevin Ryan out of our FBE Portland office. A build-out analysis is a model of community growth and development. It takes development constraints into account and projects future development based on the area's current population growth rate. And for this project, we ran what we call a full build-out model. And full build-out is a theoretical condition which represents the period when all developable land has been developed to the maximum conditions permitted by local ordinances. And we determine the amount of developable land by excluding areas with existing buildings, which are shown as red dots on the map, conserved land, which is shown as green shading, water wetlands, shown in yellow on the map, hydric soils, shown in brown, and very steep slopes, which are shown in brown hashes. The model showed that 16,772 buildable acres exist in these watersheds, which represents about 56% of the watershed areas. So from there, the model also considers current zoning. Each town has different zoning regulations, such as minimum lot size and setback distance, which are input to the model. And then the model is able to determine how existing parcels could be potentially further subdivided. And then the model places a theoretical building on those subdivided parcels. Next slide. So the map on this slide shows the results of the analysis. The existing buildings are shown as red dots and projected new buildings as yellow dots. And in the lower left-hand side of the map, you see the inset shows placement of projected buildings at a smaller scale. Areas in green are buildable area, and the existing lots were further subdivided to the minimum lot size under current zoning regulations for each town. And then placement of projected buildings were then estimated spatially based on a number of factors that we plug into the models, such as each town's setback distances. It also considers lot spacing efficiencies, things like that. I do want to emphasize that this build-out analysis is a model, and just like any model, is not meant to be a precise indicator of where future development will occur. And so it shouldn't be used at such small scales, but rather for larger scale planning purposes. So the model ended up estimating that the total number of existing buildings in the watershed were about 2,910, and we show the breakdown by town on here. And then the total number of projected building in the watershed areas totals 6,385, and again with the breakdown by town shown. And so note too that these projected buildings are in addition to existing buildings. Next slide. We then completed a timescope analysis to predict when full build-out could be reached based on compound annual growth rates for the last 20, 30, and 40 years in the watershed towns. The most recent prediction was for the 40-year compound annual growth rate at 2.23%, showing full build-out as early as 2072. This analysis shows that if growth rates, zoning, and other development constraints remain constant, the Moultonborough Bay and Winter Harbor watersheds could theoretically attain full build-out within this century. Next slide. So these build-out results are extremely helpful to watershed communities. The analysis is really a decision support tool designed to help planners and resource managers visualize, analyze, and communicate about land use decisions. It's also a powerful educational planning tool that can be used to inform future planning efforts in the watershed, guide future development activities, target specific areas for conservation, and also understand how current zoning regulations will affect future development. Lake Wentworth is a great example where the town of Wolfboro took immediate action to change zoning to better protect water quality as a direct response to their build-out analysis results. Next slide. And finally, we were able to take the results of the build-out analysis and plug them into the lake nutrient model to simulate water quality conditions in the future, sort of simulate a worst case water quality condition. And then we also simulated water quality prior to human development, or sort of the best case water quality condition. So the figure on the left shows the total phosphorus load for both Moultonborough Bay and Winter Harbor for the three scenarios: pre-development, current, and future simulations. And it shows, increasing loads with each time sequence simulation. And then similarly for the figure on the right, the in-lake total phosphorus concentration increases significantly from each simulation. These results indicate that the water quality of Moultonborough Bay and Winter Harbor could be much different than today with business as usual development in these watersheds. Moultonborough Bay and Winter Harbor would be at much higher risk for reduced water clarity and greater nuisance algae and potentially toxic cyanobacteria blooms, which represent a public health risk. These, it's important to note too that these predictions don't account for climate change, which actually may and has been shown to potentially worsen the occurrence of these blooms regardless of nutrient input. So these are all important considerations to take into account, and were taken into account when setting the water quality goal for each of these water bodies. So I'm going to hand it back over to Maggie to talk more about that.
Great. Well, thank you, Laura. So after talking about what's going on in the watershed and some of this modeling, I wanted to briefly touch on taking that next step to set a water quality goal for Moultonborough Bay and Winter Harbor. So we actually chose to set 2 goals. And so we thought that was important because that first goal is really to think about phosphorus, and it's thinking about keeping nutrient inputs to the lake low. As Laura just mentioned, we have these cyanobacteria blooms occurring, and we have relatively low total phosphorus against state criteria. But we can expect that there will be future inputs of phosphorus from, expected and necessary development in the watershed. And so what we did is set a 5% reduction target in current total phosphorus loads that will allow those 2 basins, Moultonborough Bay and Winter Harbor, to meet an average seasonal deep spot concentration of 6.7 parts per billion and 5.9 parts per billion. That second goal is really getting at the gliotrichia and cyanobacteria problem in Lake Winnipesaukee. And so our second goal is to really push and move forward with assessing both the spatial and temporal over time distribution and causes of gliotrichia blooms that we're seeing in Lake Winnipesaukee, and most notably to this in Winter Harbor, and to determine geographically specific water quality objectives in order to reduce the occurrence of these localized blooms. So the next part of the plan, and the purpose of the plan, is to take this information and make some recommendations for water quality improvement. And so what we do is we create an action plan, and the action plan has strategies, and the strategies for implementation and making change are binned in these 5 categories. So we have water quality monitoring, watershed and shorefront best management practices, road maintenance and training, municipal planning and conservation, and septic systems. I'm just going to touch on a few of these as examples. The plan is a much more extensive list of strategies. So here on this first slide, what you can see is getting back to that conversation about algae blooms and trying to understand the differences in lake dynamics and nearshore environments, is to look at to create some investigative studies in those nearshore areas that look for localized sources of phosphorus and maybe some cyanobacteria hotspots. Then kind of in tandem with that is the idea of creating a long-term erosion monitoring program. So looking at the shoreline and trying to understand how it's changing, because the shoreline itself is going to be contributing sediment and therefore nutrients into that lake. As Pat mentioned earlier, gathering more volunteers to expand and assist in that baseline monitoring program. There is a lot of variability and dates collected for different sites, as Pat mentioned. So really, like, getting a good volunteer base to help sample water quality is crucial, and it's really fun. I love going out and doing this work. It's a complete blast. Also is consider expanding the lake monitoring and the tributary monitoring programs. So maybe not just looking at summer, but, and this is already being done in some areas of these basins, but looking at the spring and the fall. Those are also critical seasons when the lake is turning over and mixing. So what's going on then? And also considering adding winter water quality sampling and data collection under the ice. A lot of new research is happening on winter limnology, which is the study of lakes, and it's really a new frontier, but what they're seeing is that there's a lot of connections between winter lake water quality monitoring properties and summer characteristics of lakes. And so we think that starting a winter program soon is advantageous. Most specific to individual landowners is implementing best management practices on your property and your landscape. It really makes a huge difference if everyone is taking those steps. So you can see on the screen here, we have some ideas of different best management practices. And again, please contact Pat or us if you're looking for some support with that. And basically these best management practices work to infiltrate, slow down water, and try to stop it from reaching the lake and carrying those pollutants into the lake. So you can do that through buffers, you can do that through infiltration steps, you can do that through plantings. There's a lot of different really unique ideas for doing this, and folks are really talented at thinking about, you know, what aesthetic do you want for your property, and making those best management practices fit. Another big one is road maintenance and training. You know, we talked a lot about sediment and how sediment can deliver phosphorus and other nutrients to the lake. So it's really important to be maintaining those roads properly so that we're reducing erosion from the roads getting into the lake. And again, as Laura talked about with the build out, taking a critical look at municipal ordinances and thinking about planning. It's one of the strongest tools to protecting lakes. You can do that through ordinances and setbacks. And we've included a conversation about that in our planning document specific to the towns in these watersheds. And you can see in this graphic just the idea that on the left, if you have a forested system, if it's developed without any control on ordinances and growth, in that middle diagram, you can see it gets really overdeveloped, and the development isn't done in a smart way. But if you are really thinking about your town's planning and conservation goals, you can set ordinances in place that will allow for smarter growth and smarter development in the watershed. So with that, I'm going to take a brief pause so everyone can stretch, and Brian's going to come on and talk about a few specific sites that they helped us with. And the hope with these sites is to maybe have a jumping off point to be able to move forward with getting some projects in the ground. So I'm going to stop sharing my screen, and I'm going to just take a minute, stand up and stretch. It's been a while, and then Brian will be on in a moment.
Well, good evening, everybody. My name is Brian Leverrier. Give you a couple more minutes to settle in. We're going to be talking about some of the concept plans and the best management practices at the sites that were identified by Forest Bell's group. give folks a couple more seconds here. Okay, well, I am going to assume everybody's back in their seat and ready to go. I think I want to say first that, you know, it's amazing how many participants we have tonight, and I think that's amazing. You know, the number of people that are interested in protecting Lake Winnipesaukee and doing the right thing. I think that's the most important thing here. And so the site that we're looking at first is right off Route 109 in the heart of Melvin Village. And we identified runoff coming off Route 109 as well as down Lake Road. And I think when we design these sites and these practices, we're always trying to embrace the existing drainage patterns. And I think to Maggie's point there at the end of folks wanting to do something on their own property, whether it's raining or it's dry and you can find gullying or erosion or sedimentation, there's certainly signs and symptoms on the landscape that show us where runoff is traveling, and then finding those opportunities to collect that runoff, perhaps before it leaves your driveway or across your garden beds or across your lawn, and dealing with it before it gets to the public right-of-way, in the drainage infrastructure, or ultimately into Lake Winnipesaukee at the end of the line. So here we identified gullying along the edge of Lake Road. And so the top image along the right-hand side shows a drivable concrete paver system that we've used on multiple projects, and it's great because it allows for maintenance to be conducted without disturbing the substrate. You can even have vegetation grow up through it, so it doesn't need to be, you know, more pavement on the landscape. And it can also attenuate the runoff, so it can slow down the velocity. And it's really the velocity and the concentrated flow that is going to do the most damage, you know, leading to erosion and then causing sedimentation downstream. And so once the water enters that stabilized flume, we're going to create a sediment forebay or a sediment trap. And that's where we're going to try to collect all of the salt and the sand and the leaf litter and trash that comes off of the road, and provide a consolidated space where maintenance can be conducted. So whenever we're designing these systems, you know, we realize that what is put on the pavement for public safety purposes throughout the winter ultimately ends up in our stormwater practices. And so if we can design these systems to allow for maintenance to be conducted, at least we've given the opportunity for it to be conducted. And, you know, these systems are only as good as the maintenance that follows. And, you know, research shows that if maintenance doesn't happen over the years, these systems fail and they don't provide the treatment that was intended. So the maintenance is critical. So once the water gets into the system and leaves the sediment forebay, then it will enter the treatment system, which on this particular site, we designed a bioretention system. And it operates the same way as a rain garden, except we have pipes and structures that protect the public, and we can control the overflow. So when the systems do reach capacity, which will happen, the water can safely leave and not cause erosion. And so this system here was designed for the full 1-inch water quality volume, and that really was our aim, to improve the water quality. And so 90% of all rain events that we experience produce the water quality volume. So this system would be able to retain rather, 9 out of 10 storms. And that 10th storm would go into the overflow structure and be safely conveyed into the lake. And with the water quality volume, that's where we see sort of the first flush of the salt and the sand and whatnot that comes off the pavement happens during that initial flush. So if we can capture and treat and control that water quality volume, you know, that's us doing our job from the best management practice standpoint. We didn't oversize these systems for cost purposes and disturbance purposes. So if we can match, you know, the water quality, that's really where we set the system. We run the model for larger storms, again, to make sure that the water is being controlled and conveyed properly and not overtopping and causing, whether it's a public safety hazard or, water's going off property onto another private property. Those are the sort of things that we're looking at and trying to avoid. We've also incorporated other practices outside of the bioretention system. So that would be porous pavement, geogrid systems that can allow for heavy equipment. Here we're seeing trucks and boat traffic. So as well, on top of dealing with the stormwater runoff, we're also complementing the existing uses and ensuring that the current land uses can be maintained, and then we can incorporate the best management practices with the leftover space. And fortunately on this one, the leftover space is where the water was already going. So that goes back to the original statement of embrace the existing drainage pattern to reduce project costs and disturbance. So image B on the right shows stabilized parking, which is a site in Rhode Island. And then the bottom one shows a vegetated bioretention system. It's a shallow depression, very simple, with native plantings that are drought tolerant, but can also take saturated soils. So with that, Maggie, I think I would be ready to move on to the next one. So that the color-coded graphic was the concept plan that we developed once the site was identified. We had our solution, and we wanted to illustrate that so we could communicate that with the association. And once we were in agreement on the sites that we wanted to advance, that's when we went towards construction-ready documents. And this is part of the set that we put together that advanced not only the site we just looked at, but several others. And this was a site that is right across the street from Lake Road along Route 109. This is within the public right-of-way. And we embraced the existing drainage patterns. We prevented the water from going directly into the existing catch basin. We wanted to utilize the existing catch basin as our overflow structure to save project costs, reduce project costs, and then develop the inlet with the sediment trap as was described before for easy maintenance. And this particular design can manage the ½ or half the water quality volume. So anything above the ½ will enter the existing catch basin. With that said, this is an improvement beyond what we're seeing out there today, because essentially 0% is prevented from going into that catch basin. So it's a direct input into the catch basin. It goes into the pipe, and the pipe sends it directly to the bay. So this system will at least prevent all of the runoff from going into the catch basin and provide some treatment up to the ½ Along the left-hand side is our first inlet with a sediment trap or sediment forebay. And then we also designed a second sediment forebay and sediment trap at the existing low point. And that goes back to embracing the existing flow patterns, because we really didn't want to, do excavation, or at least we wanted to minimize excavation. We wanted to protect the tree to the best, the greatest extent practicable. So that led to a very shallow system. We could have dug this deeper to try to get the full water quality volume, but we thought maintaining that tree and not making this system too deep was important from a safety standpoint. We did design a broad crested spillway, which is stabilized. So when the system does fill up, it'll cross over that stabilized spillway. And obviously it doesn't have loose aggregate soil, so it won't be able to erode. And so when this system does hit capacity, we could start to see higher velocities once we can attenuate the flow inside the forebays because they're full of water. On the left-hand side, you're seeing construction details. So we have those called out on the plan wherever they are applied. And a construction detail shows us the materials that are needed, the depths that are needed, the dimensions that are needed, and how each element goes together. So it's really the recipe of how are we going to build this and what materials are needed. And I think with that, I'm ready to go to the next slide. So we're back to the concept sketches here, and this was a site identified along New Road where there's an existing culvert, and it's a box culvert, a concrete box culvert. And what we observed is that the runoff along New Road was failing to get off the edge of pavement for a number of reasons. The shoulders were high, there was leaf litter and pine needles that were accumulating along the edge of pavement. So it was preventing the runoff from getting off and away from the edge of pavement. We call that positive drainage. And because of that, the runoff was getting all the way to the concrete box culvert, and that's where it met its point of least resistance, and then it started to run downhill. By that point, we had quite a bit of volume that had accumulated, and the slopes are very steep and sandy loose aggregate. So you've got the worst case scenario of concentrated flow on unstabilized soils with very limited vegetation. So we were seeing gullying, erosion, and all that sediment is finding its way into the river. So the sequence of solving this problem would be first controlling the road runoff and allowing positive drainage so that the runoff can exit the pavement off the edge of the pavement well before it gets to the culvert. There were already 2 existing swales there today, so all we really needed to do was provide the flow path, the mechanism for the water to find its way into the swale. And you're seeing that along the northern side where that existing swale is shown. And the picture in the top right shows an example of a stabilized edge where you've got that 45-degree chamfered edge that it would be very hard to accumulate that much leaf litter and sediment to prevent the runoff from coming off the edge of pavement. Once it gets off the edge of pavement, in that particular instance where the swale exists, the water is going to follow the path of least resistance downhill. The swale channel was wide enough. We recommend a minimum flat width of 3 feet, and that's going to try to negate concentrated flow. The narrower that channel bed is, the more the water is going to follow one fine line and thus potentially cause erosion. On the downhill side, the southern side of that box culvert, there was an opportunity for a rain garden. So beyond just a swale, again, we wanted to provide positive drainage off the edge of pavement. But if there was space available, which in this location there is, within the public right-of-way, we designed a very shallow rain garden. And you can see in image B is a formal rain garden that we designed on Cape Cod, where you can see the sediment forebay, the sediment trap, with that same drivable grass product, so that can be shoveled out quite easily. That granite curb is our weir, so that's going to retain that initial flush in the forebay, and that will catch a majority of the sediment and the trash and the leaf litter. In behind is the treatment system, so once the forebay fills up, the water will then cascade into the rain garden, where it'll be treated primarily by soil, but also the plants are going to work for us too. And then along the right-hand side of that image, you can see the stone and another granite curb, and that's our overflow structure. So that we call a level spreader. So when the water fills up this whole system, if you can imagine, it's going to go towards that curb, and that curb is going to encourage the water to flatten out and spread out, and we call that sheet flow. So if we didn't have that curb, there would be a chance for the water again to concentrate. And although we've provided great treatment and we've provided an awesome opportunity to conduct maintenance, on the downhill side of the system, we could see more erosion. So I would say that's a very important thing to these, is not only the maintenance at the beginning and throughout, but also just be observant. And if you observe issues like sedimentation or erosion, the system might need to be modified to negate whatever issue we are seeing. And we have installed these, and observation and monitoring, as we've discussed tonight, is very important, not only before implementation but also after. I think that's probably it for this one, Maggie. And then this is another exciting project. This is along Northwoods Road near the YMCA camp. And this is probably the most simple design of all of them, because there's no structures required, very little disturbance, no vegetation needs to be removed. And again, we're just embracing the existing flow path and preventing the runoff that goes off this dirt road from entering the stream directly. So we're giving a very shallow vegetated rain garden. You can see image B is a really good example of what this could look like. And this will allow runoff to safely come off the road into a sediment forebay, over a check dam or a weir, and flow into the treatment area. This system was designed to capture the ½ inch, mostly because the drainage area is quite large, and they have existing erosion issues there already. And if you walk up Northwoods Road, you can see some of the methods that they've taken in the past to break up that flow path. So this would be another example of breaking up the flow path, attenuating, slowing down the velocity, and then safely conveying it into the stream. And you can see at the end of this one, we also included a level spreader, because once the system does fill up, we want to safely convey in sheet flow as much as we can the water back into the stream. And I would also say, I think this site is a really good example of, an opportunity to get the youth involved, be it at the YMCA or maybe at a local school. Raising awareness and getting the youth involved, I think, is probably our most important tool to not only deal with these issues today, but also as we move forward into the future. And I do have a question about clarifying site 101A versus 101B. So 101B was based on the last input session that we had. There was a comment that, really we want to focus on work within the public right-of-way. And so we adapted our site with 101A, which is at the boat launch in Melvin Village, to incorporate a best management practice that was entirely within the public right-of-way. And so that's where we pivoted and we identified site 101B, which is right across the street, using a lot of the same materials and details, but can be done fully within the right-of-way. And I think that was the key difference between those two sites and the reasoning for why we designed them. I'm not sure if anybody else has any questions directly for me, but I'd be happy to answer anything I can.
Thank you, Brian.
Thank you.
So we have just a few questions that have come in over the meeting that I'll bring up. And for anyone that needs to leave, we will make sure this is recorded and we'll make sure to have the questions listed so you don't miss anything. But the first question was asking if there's grant funding available to complete best management practices. This question was asked early on in the conversation. We've talked a bit about that, and absolutely these watershed plans set you up for accessing future grant funds with EPA. That is part of the goal of doing this. Pat, did you want to add anything to that?
No, Maggie, I think that's right. Once you have your management plan in place, it opens you up for future funding. Yep.
Great. And then there was a question about the modeling. Laura touched a bit on this, but Lauren, maybe if you want to expand, or Dawn, someone asked what the largest contributors to the total phosphorus load are. Is it lawn fertilizers, or is it other sources that we're seeing in the watershed?
Yeah, well, Dawn hasn't had speaking time yet, so I'll pass. I'll lob this easy question to you.
Yeah, sure. So I'm happy to take it. So I think probably, if we added up all the sources, the number one source would be the change in land cover from forested land to developed land. Just that inherent change in land cover increases phosphorus export by about 10 times. And that includes, everything from rooftops to driveways to lawns. It also includes lawn fertilizer. It's sort of that developed landscape. Now, there are ways to develop to make it look more like a natural forest or function more like a natural forests, and those are the things that we really would encourage people to look into when they're developing or redeveloping property. But I'd say the change in land use is probably the biggest source, and that's distributed throughout the watershed. Although, you know, in the lakes region, most of the development is close to the lakes. So it's kind of a double-edged sword in that, you know, not only are the sources there, but the sources are very close to the lake. So there's not a lot of opportunity to infiltrate that water that's carrying the phosphorus before it gets to the lake.
Great, thank you, Don.
Mm-hmm.
Does anyone have any additional questions they want to ask? I don't have any others oh, when I got one just now. So when thinking about the surveys from the watershed and the comment from Don, is there best practices for homeowners to access and consider?
Absolutely. And probably the simplest first step is to do participate in the Soak Up the Rain programs that New Hampshire DES provides, where they'll send somebody out to take a look at your property and look for simple solutions that homeowners can do themselves to infiltrate water and create buffers and fix, you know, existing simple problems on your own property. And you know, those visits, we've done a whole bunch of them over here around Lake Wentworth. You know, they're fairly quick, a half a day, and they give you some great ideas for what you can do to make your property better.
Okay, great. We have a question from Crystal. How can the smaller local lake associations best support these efforts? Do you want me to go?
I can do it, and I think Pat should probably also address this in maybe a little more detail. But I think that we get grants, and I see Kate mentioned this too, is we get grants and we apply to the EPA, but what we really need is for the community to also donate to get these projects done. EPA funding is only going away, it is not increasing. So relying on that is something that LWA has not been enthusiastic about. We do rely on it, we're very grateful for it, but you know, it's going to take us 1,000 years if we try to do these very simple projects if we wait for all of these applications for grants. If people are donating to us and we have the funds ready to go, we can react much more fluidly, no pun intended, and we can also you know, prioritize that. We've already prioritized these things in the reports, but we need to prioritize and select things that maybe it was prioritized and we didn't know it was going to happen or it wasn't possible, but boom, all of a sudden we've got the money. We can't wait to get over 1,000 sites addressed. And it is important, LWA on its website, and we have a flyer for it. We have a 10 things, not 10 things, but how you can help the lake. And it's basically the suggestions, and it's a list spelled out, Lake Winnipesaukee, and every single letter has a suggestion on what you can do for your own property. And I think Pat probably has a few more ideas or might want to add something.
I was just going to add that, yes, Lake Winnipesaukee Association has been working with the residential homeowners. Last summer, our AmeriCorps members went out and did 46 residential site walks with people to give them recommendations on what they can do. So we offer that service. I have a flyer handout that FB has helped put together as part of this project, but we are doing that, as well as New Hampshire Lakes also offers that same service to lake associations or lakes, you know, throughout the state. So there are a multitude of available resources out there that people can tap into.
Great, and then we had added into the chat here, let me pull this up. From Kate, while grant funding will be helpful to implement these in future action plans, we can't rely solely on this funding, and it will take individuals, businesses, and our member contributions. And Kate looks forward to talking with anyone that wants to participate in that meeting or discuss further. So feel free to send Kate a private chat if you want, or reach out to Kate at her email. Okay, great. So we have a question here. If you are trapping the phosphorus in a rain garden or other structure, does that concentration need to be controlled or periodically dug out and disposed of? Do you want to take that maintenance question, Brian?
Sure. Well, the soil and the plants are going to deal with it. So you can, I think in the rain gardens and the bio, we did mostly perennial based landscape design. So at the end of the season, say in November, you can go in and you can cut all of the perennials. You can bag them if you want, and you can remove them from the site. In terms of the soil, we really don't want to disturb the soil media at all if possible, because it is a specialized sandy loam mix that is intended to infiltrate water. So I wouldn't recommend, really tilling that soil at all to deal with the phosphorus that's caught up in the soil. But in terms of the phosphorus and nitrogen and other elements that the plants will absorb, that's the beauty of going with perennial-based plantings, because they'll utilize those and then they can be cut back, removed, and they'll grow right back the next spring as strong as ever.
Does anyone have any additional questions? I don't see any others in the chat, so I hope if I missed you, please speak up, and I'll open it now since we're at the end of the meeting. You can, turn your mic on if you want to make a comment or ask a question.
So Maggie, I'll make one more comment, and this is sort of on
Please.
the what we can do end of things. And I think thanks, Pat, for reminding me that the Lake Winnipesaukee Association was also doing shoreline or shorefront property audits. That's a great thing. So we're entering in New Hampshire the end of road construction season, and I think there's a real opportunity in working with your local transportation department, local public works department, and if you look at where their sites are distributed that we're looking for to improve with BMPs, they're often along highways. And if you can do that in conjunction with a road reconstruction, for example, Main Street in Moultonborough is being reconstructed. There are numerous others around the watershed that are being reconstructed. Make sure that sites that have been identified that are along that are reflected in the plans to do it, because you can do it all as part of an existing project, and it ends up being a whole lot cheaper and a whole lot easier to facilitate. But you have to be aware, because I think if the DOT is just putting together the standard plan, it may or may not include all the water quality enhancements we want to see. So make sure you're taking a look at the plans, go to those public meetings, and see if you can incorporate some of the low-hanging fruit there.
Does anyone else have anything to add before we wrap up? Pat or Diane or Kate, do you have anything you want to add before everyone leaves us?
Just want to say thank you to FB. Great presentation, Maggie, and to the team. And we really appreciate everyone joining us tonight for this.
Great. Well, thank you, everyone. Laura, do you want to stay on for just one moment so we can make sure we save everything properly? And have a wonderful evening. And oh, Diane has one thing.
I am sorry. I just saw a really good question from Wayne Doman. And it says how to monitor septic systems 25 years plus. We could get in touch with Wayne.
Okay.
Or we could answer it now. Either way.
Go ahead.
So, well, Pat sort of knows about what to do with this, so I'm going to let her talk about it.
Well, really, if it's a system that's over 25 years old and you have some concerns, I think The only thing you can really do, or the best thing you can do, is really get a licensed septic system evaluator to come out and look at your system and do a true evaluation. And they'll let you know whether it's working or not. So for the money, that's going to cost $250 to $500. There's a range, but that's the best thing a homeowner can do. And give you some peace of mind, hopefully.
Okay, great. Well, thank you, everyone. Really appreciate your joining us. And thanks to Pat and Diane and Kate for all that you're doing for the lake.
Thank you. Thanks for
Maggie.
everyone coming.
Yep.
Have a nice night, everybody.
Right.
Good night.
Good night.
Thanks, Maggie.
Thanks, Diane.